Welcome to Direct Current Deep Dive, exploring the technical framework of Current OS, a MOOC designed to dive into the principles behind Current OS technical decisions and their role in defining the electrical standard for DC microgrids. This video is part 6 of a 6-part series. Explore the remaining videos on the Current OS YouTube channel to continue learning about the world of direct current. In this video, we'll explain the underlying principles that drive Current OS's technical choices regarding earthing, as it is commonly referred to in British English, or grounding in American English. For consistency, we'll use earthing throughout this MOOC. We understand that this might sound unfamiliar to our American audience and appreciate your understanding. The aim is to isolate the DC installation from the AC grid for stability. Current OS solution makes DC applications safer, simpler to design, and more immune to external issues. By eliminating the need for continuous specialized maintenance, it is particularly well suited for commercial and industrial applications. Earthing in a DC system is a critical topic, and Current OS has established a key rule that the IEC is in the process of formalizing. A DC system can only have its own independent earthing network if it is galvanically isolated from the AC system. The core principle of Current OS is therefore to isolate the DC installation from the AC grid, preventing disturbances and faults from propagating between the two systems. Without isolation, the DC system effectively extends the AC earthing scheme. This would be posing significant risks. For example, if there are DC current leaks into the AC network, they can saturate transformers. Even just a few hundred milliamps can saturate a medium voltage, low voltage MVLV transformer, creating a highly dangerous situation. In the opposite direction, if AC current leaks into the DC network, it can generate voltage transients that may damage electronic systems and converters. Failing to isolate DC from AC requires additional precautions and protections on both sides, which are complex to implement. For this reason, Current OS does not recommend this approach. Corrosion mitigation is also an important element, and Current OS addresses this issue. So Current OS mandates galvanic isolation between AC and DC systems. Additionally, Current OS recommends a TNS configuration or single-point grounding for the DC side, earthing the midpoint of the DC voltage band. It's also essential to implement corrosion mitigation measures. This is why Current OS prohibits the use of TT earthing for DC installations. While TNC and TNCS systems can technically be implemented, they require significant precautions, making them less favorable. IT earthing or isolated grounding is also an option but has not been documented by Current OS. The IEC does not recommend IT earthing for commercial buildings. In the event of a DC earth leakage to ground, it's generally better to cut the power and allow a maintenance team to address the issue. In industrial settings or hospitals, where uninterrupted energy availability is critical and a dedicated maintenance team is present 24/7, IT earthing may be suitable. However, in commercial buildings, where on-site electricians are not available around the clock or may lack the required expertise, TNS is the simplest and most effective choice. That is why Current OS recommend the TNS configuration for its DC installations. Here is the recommended approach from Current OS for connecting to an AC system. The setup typically involves an AC system connected via an isolated converter or a transformer, followed by an AC-DC converter. This configuration is common practice, using a transformer to provide isolation and then converting AC to DC. The term converter is used instead of rectifier because energy flows are bidirectional, allowing power to move both ways when needed. Next in the configuration are the fast-acting electronic protections. The system connects the M point to the PE, protective earth. Whether it's called a midpoint with a positive and negative pole, or simply M without a negative pole, the principle remains the same. One key advantage of this setup is that electronic protections only need to interrupt a single conductor. This is twice as cost-effective compared to IT systems, where both conductors must be interrupted. It also results in lower energy losses and reduced heat generation. Finally, power is supplied to the DC converters. With this arrangement, issues related to DC earth leakage currents are resolved, ensuring the installation is both safe and sustainable. To summarize, these are the Current OS preferred earthing systems. For buildings, a unipolar system is often used to power devices such as LED drivers, computers, and the building's telecom infrastructure. For instance, it might distribute 350 volts. A bipolar system, on the other hand, is suitable for powering higher demand equipment. In this case, 2 times 350 volts could be distributed to applications like heat pumps or elevators. This system can be implemented with or without a distributed midpoint. This concludes the earthing presentation of Current OS. Want to learn more? Check out the other 5 Current OS MOOC videos covering an introduction to Current OS, voltage bands, power management, electrical protection, and pre-charging. Thank you for watching.